the mic. Well, thank you very much for coming. I don't know if there is many people online or not, but welcome. And thank you very much to Niratana for accepting to be here in this LOCA series. I think it's better you introduce yourself. Yeah. You will do it much better than me. But she's a PhD student with an FPI, also within the Severo Ochoa project, and contributing to improving the communication between the different departments. So all yours.
So yeah, thank you. My name is Niranjana Sriram, and I'm a PhD student in the Propulsion Technologies group of CASE department in BSc. Today.
A ver, y si sales de pantalla completa. Vamos a probar.
Sí.
Ahora, perfecto.
Today I'll be talking about the development of advanced Soot models for non-volatile particulate matter produced by aircraft engines using advanced computational models. So I'll be presenting some of the work which I've done, as well as some of the work which has been done in the group. The context. So fossil-based fuels have been the primary source of energy conversion for like ages. But one of the main disadvantage of having hydrocarbon fuels is that the combustion produces harmful byproducts with its emissions. So out of that, we know that carbon dioxide is one of the major emissions, which is a greenhouse gas, and it causes global warming. Out of that, there are other byproducts as well, out of which one is soot, which is basically carbon nanoparticles. And soot causes like serious health risks because they're carcinogenic and they lead to different respiratory illnesses. And the other disadvantage of soot is that once it gets deposited, then it can reduce the efficiency and also affect the performance of any combustion system. So because of these reasons, there is a need to better understand soot formation and also bring improvements in the models to understand and also mitigate soot formation. So that's the introduction to what exactly soot is and how is it formed. So soot has been studied like extensively over the past decades because of its health and environmental hazards. So basically, as I mentioned, soot consists of carbon nanoparticles that are generated because of hydrocarbon combustion, and it's a very intricate and multi-stage process, which I'll be explaining now. So the soot, first it forms from initially the fuel breaks down to form aromatic rings. This process is called fuel pyrolysis. So these aromatic rings are called polycyclic aromatic hydrocarbons. So the first soot particle is formed when two polycyclic aromatic hydrocarbons combine. This process is called nucleation. So this gives the birth of a soot particle. Once we have a soot particle, the formed soot particle, it combines with a polycyclic aromatic hydrocarbon to form a larger soot particle. This process is called condensation. Then we have acetylene in the environment. So this combines with the soot particle at the surface, and it again leads to growth of the soot particle. This process is called surface growth. And once you have enough number of soot particles, then two soot particles, they can collide and form a larger soot particle. This process is called coagulation. And once like a soot particle comes in contact with either oxygen or OH radical in the environment, this process eats up the soot, consumes the soot which is being formed. This process is called oxidation. So these are the steps which is basically involved in the formation of soot. So as I mentioned, soot has been studied over many years and across different length scales. So first, in the micro scale, we study the soot particle interactions between the soot molecules. So that's the lowest form of this. So we have two different types of models. So discrete element soot model and also molecular dynamics. So In this case, we study how two soot molecules interact, the molecular forces, the van der Waals forces, and the intermolecular distance between two particles. When we come to mesoscale, it's just an overall representation of soot. So in that case, we have the Monte Carlo method, which gives us the particle size distribution of soot. But this method is computationally, it's very intensive. And then we have the discrete sectional method. In this case, the soot particles are divided into sections or bins, depending on its size. Under this, we have two types of models, the univariate and the bivariate sectional model. The other method is the method of moments. In this case also, we'll be getting the particle size distribution of the soot particles. But the disadvantage with the method of moments and the quadrature method of moments is that we don't get real-time information of the soot particles. So this advantage was overcome in the direct quadrature method of moments, where we get real-time information of the particle size distribution. And then the higher scale is the macro scale, where it's a semi-empirical or semi-empirical model. So in the one equation soot model, you just solve one equation for the entire domain, which is for the soot mass fraction. And in the two equations soot model, we solve for the soot mass fraction and the radical concentration. So in our group, we specifically focus on the discrete sectional method and specifically on the univariate and the bivariate sectional method. So when it comes to the univariate sectional method, we solve only for one equation in each section, which is the soot mass fraction. And when it comes to the bivariate sectional soot model, we solve for two equations per section, which is the number density of agglomerates and the number density of particles. So the extension from the univariate to the bivariate soot model was a need, because the univariate soot model, it considers soot particles to be spheres, which is a very crude assumption, because as seen from the figure, from experimental data, we can see that soot particles are not spheres, but then they have some sort of a fractal shape. So so we can't consider it as spherical particles, which is why we'll have to shift from the univariate to the bivariate soot model. So in this case, so when it comes to the univariate soot model, we divide the particles in terms of volume. And in case of the bivariate soot model, we divide it into sections in terms of mass. And yeah, in univariate, the main assumption is that it's spherical particles. And when it comes to bivariate, we consider it as particles with a fractal dimension of 1.8. And the univariate, it solves one equation per section, which is the soot mass fraction. And the bivariate discrete sectional model solves two equations per section, which is the number density of particles and agglomerates. So the main objective of the work which I'll be performing is to develop models for predicting soot formation from aircraft engines. And to reach this objective, we have divided the work into the following. So the first thing will be to extend the existing univariate model to the bivariate soot model. And then we'll be studying the effect of the different processes which I mentioned before on soot formation. And then we have a tabulatory chemistry model in our group. So we'll be adding a transport equation to that to see how that affects soot formation. And also on the applications perspective, initially it'll be gaseous fuels, but then we'll also be shifting towards liquid fuels as well. So yeah, so as a first step for going from the univariate to the bivariate model, code in 0D code in Python was developed. So basically we'll be going from 0D to 3D, which is the most realistic cases. So in terms of complexity, we have 0D cases, 1D cases, and 3D cases. In case of 0D, we work with a plug flow reactor, and in 1D, we have premix laminar and spray flames. And in case of 3D, we have realistic burners like from Cambridge and also the CRSP. So when it comes to the 0D plug flow reactor, so basically it means that we don't have any variations in the transverse direction. So that's why it's called 0D. So to for the code development, temporal transformation was applied, and we solved for the species and the temperature. And also, depending on whichever Soot model, either the univariate or the bivariate, we solve either one or two equations for each of the sections. So the validation of the 0D code was performed with the existing Soot library in our group. So this one is the results for the univariate. So this was to get a confidence that the code which was developed in 0D works well with all the already existing code. So the next step was to check if the 0D code works well for the bivariate model as well. So for the bivariate model, we have this nanoparticle plug flow reactor, which is the open source code. So the 0D code was compared with the result from the nano plug flow reactor. Next, when it comes to 1D, the initial step was to compare the 1D premix flames. So we just took a normal ethylene as fuel and air as oxidizer. So we have, so there's another software developed in Eindhoven, which is called Chem1D. So this solves for 1D premix flames, which we used as a comparison to validate our premix flame simulations. So the initial step was to make sure that without Soot, we have a proper results which matches. So just plot the basic species which are involved in Soot and also the temperature to check if the evolution matches. So without Soot, they matched well. So the next step was to go to with Soot. So when it came to with Soot also, we just plotted the species which are involved in Soot. So basically pyrene, which is the PAH, and also C2H2, which affects surface growth. And also finally on the left hand side, the last figure is the Soot volume fraction. So basically we had good comparison between both Chem1D and Alia. So 1D premix flames worked well. So the next step was to switch to spray flames. This one is to bring into applications perspective, because finally in any combustion system, you introduce liquid droplets in terms of spray or injection. So which is why we had to shift to spray flames. So in terms of spray flames, we took two fuels, Jet A, which is the normal aviation fuel which is used, and SAF. So SAF is sustainable aviation fuels, which is the trend nowadays because we are moving towards more environment friendly fuels. So basically sustainable aviation fuels are synthetic fuels which are produced to reduce the pollution which is caused by the existing aviation fuels. So these are some very preliminary results between Jet A and SAF. So we can see that in this present case, so the SAF which we are using has a higher aromatic content. So which means that when you have higher aromatic content, it means you have more PAHs, which means that obviously you're going to have more soot formation, which is what we will see on the soot volume fraction figure. And also you can see that the pyrene level and also the naphthalene level, which are PAHs, are more in SAF compared to Jet A. The next thing is coming to 3D in terms of burner configurations. So this is a CRSB burner which uses liquid N-heptane as fuel. And yeah, this is how the burner is. So coming to tabulated chemistry in the group, so there is two ways of the tabulated framework approach. One is in FGMC, in which the species mass fraction are tabulated and the Soot systems are calculated during runtime. And then the other is the FGMT, where both species mass fraction and the Soot systems are tabulated. So the need to shift to tabulated chemistry was to reduce the computational cost, because we're solving for a lot of species and we have a lot of equations. So when it comes to tabulated chemistry, the computational cost comes down. And also, in addition to this, clustering model was introduced, which means that depending on the number of sections, you could cluster the sections into some like a reduced number, which will further reduce the computational cost. So in this figure, you can see the difference between the time taken to run a direct chemistry and a tabulated chemistry simulation. So it's obvious that like when we run tabulated chemistry, it takes lesser time compared to the finite rate chemistry. So yeah, so when it comes to tabulated chemistry, we just run 1D flamelet solutions with Chem1D, which is like very easy and it's very quick. And we generate a table from those 1D solutions, and then we couple it with the CFD, and you just look up into the tables for the source terms and values, which when calculating the CFD, it's easier. So the progress of Soot modeling in our group. So initially, the first step was to check if the tabulated chemistry works with the sectional Soot model. So once that worked, the next step was to implement it or try it with the flames which are there. So the flame which was tested was the Sandia flame. And then the next step was to see if the clustered DSM model works. For that, the flame used was this RQL burner and the DLR and Cambridge RQL burners. So these are just some results for the Sandia flame. So Sandia flame is just an open flame. It doesn't have any, it's just open in the environment. It doesn't have any bounding conditions. So in this case, it will be used earlier to run it with LES and the discrete sectional method, and it was tested for both the tabulated chemistry approaches. So these figures, they show the instantaneous fields of the species and temperature. And on the left-hand side, we can see the Soot volume fraction for comparison between the experiments for both the approaches. This still shows that the Soot modeling is still like it still needs improvement, because Soot is very difficult to capture, and it's very intermittent. So we still need to try and improve the models. So
Just in this case, the ideal scenario would be the dot line, or
sorry,
so you said it needs to be improved.
Yeah.
But what's the ideal case? So what's the expectation?
No, there's not.
Okay.
The dotted one is the experiment.
Okay.
So we're just comparing it with the experiment. So as of now, we have like some match between the experiment, but Soot is very intermittent and it has a very low residence time. So we still need to improve on how can we capture it well.
Okay.
Yeah. So one of the major outcomes of this thing was when you use FGMT, the simulations are almost like we had a speed up factor of 7 times. So which showed that FGMT is like computationally very strong. The next one is the DLR RQL burner. So basically you have the fuel coming in through the center, and then you have air coming through the swirlers, which forms the flame. So in this case, the clustered sectional model was studied with the FGMT. So the experiments were for 2 different operating pressures. So in this case, between comparing the experiment and the LES, we could get a very good spatial distribution comparison, and also the peak values, which is concentrated in the center, that was also captured. The Cambridge RQL burner is an experimental test rig. So in this case, we just have a non-premixed ethylene frame. And in this case also, we studied the clustered DSM with the FGMT. So even in this case, if you see on the left-hand side, it's the radial profile of Soot along the different axial locations across the flame. So this was pretty well captured. And even in this case, so there was up to 6 times speed up factor when you ran with FGMT. So the last thing which we are working on is the CRSB. So this is also a realistic gas burner. So in this case, when we run the simulations, we are able to overall capture um, the distribution, but if we compare it with the experiments, the soot volume fraction is, so the soot is more downstream in the experiment compared to what we get from the LES. So we are looking into what reasons could be there. So when we check the source terms, we could see that the nucleation source term was high in the place where the soot is produced in the simulation. So we are trying to improve this by adding efficiency models to the nucleation model which is already there. And also we are trying to integrate a pH transport equation into the already existing tabulated chemistry to check if there is any improvement in these results. So far, we have a good agreement with the models in ALIA and PFR for the 0D code. And as I had already mentioned, SAF produces more soot, but that's because we have more aromatic content in SAF, in the SAF which we are using now. And as an ongoing work, we're studying new models to improve the results which we saw in CRSP. So, yes. Yeah. Thank you.
The increasing proportion of aromatics in SAF compared to J81 is translated into a similar growth of soot production. The proportion is kept, or it's kind of exponential? You have, I don't know, 9% more of aromatics in the SAF, and this triggers the formation of soot, and you get much more soot.
No,
Before you answer the question, could you repeat it more or less close to the mic, because I'm sure that people online probably cannot. Oh, but you can go there. Yeah. She can repeat the question, or you can go.
there, anything is okay.
Go. You have time.
Yes, the question is, in which proportion the soot increases in SAF compared to Jet A1? I mean, this proportion, the proportion that it increases the soot is in line with the increase of aromatics, of higher atom aromatics that you have in SAF compared to Jet A1.
So yeah, so this is ongoing analysis. So it's just that as of now we are using SAF with higher aromatic content. So I'm still not sure if it's like equally like adding up to the soot formation. So that we'll have to check.
Maybe.
¿Cómo estar ustedes?
Maybe I've missed it before, but these models you've tested in 1D and 3D with ALIA, right?
Yeah.
Is it like the uni or the bivariate?
No,
or both?
No, yeah.
Okay, so the bivariate is, you say, consider non-spherical particles.
Yes.
Are you thinking of testing this one or not? Is out of the scope of your project?
It's just that I haven't added the results here, but yeah, I'll be testing it for the 1D planes. Yes.
Okay, thank
Yeah.
you.
I think this is part of your PhD work, right?
Yes.
So what's the end goal of the thesis, and where are you right now?
So the end goal, so the main point was to like develop a new model. So the bivariate model is what I'm developing, meaning that's developed. So the point is now to see how the univariate results, which is already there, it changes, or whether it changes, or whether there are improvements when we include the bivariate soot model in the yes.
And for the simulations, we're using Manhattan 5.
Yes, Manhattan 5.
I assume it's the general purpose partition, or are you trying also to use some of the acceleration partitions?
No, it's the normal.
Okay.
Yeah.
Okay.
Mm.
And probably it's more.
Yeah, there are
it would make sense to in the future, if probably it will depend also on the models, how you develop the models later to see if it
Absolutely.
makes sense.
Yeah.
What's
Yes.
the explanation. Okay. Good. Is this? Okay. Is there any question? Sorry. No worry. Is there any question from the people online? Bye.